So hello everyone, so welcome to the talk. First of all, I'm Zhi Yee from the University of Malaya. So this is a talk with the title Where the Tree Meet the Well, A Journey in Graph, Ramsey Theory. So this is under the field of mathematics. So more specifically is under the graph theory. So this is a joint work with the Thomas Briggs from the UNSW Sydney and also with the Professor Wong from the University of Malaya. So before we continue, please allow me to hide myself so that we can have a better view on the slide. Okay, first of all, what is the randomness? Okay, so as you know that the randomness it can mean that the lack of the patterns or the predictability of the events that occur by random chance rather than by the design. So what if now I tell you that a complete randomness is impossible, or at least it can be eradicated or destroyed? So this is proposed by the mathematician called Ramsey at 1928. So Ramsey's theory stated that if a sufficiently large mathematical structure is cut into pieces, then one of the parts must have a given interesting property. Interesting that property that we want. And as you can see that Ramsey is born in 1903, and unfortunately he died very early at the 1930, so at the age of about 27. So the most significant contribution is actually by the Paul Adus. He's a Hungarian mathematician. So, however, although the much of research has been done throughout from the 1928 up to today, however, the progress has been painfully slow. So one of the very typical examples is in a party of 6, so let's say a group of 6 people, so there must be 3 mutually friends or 3 mutually strangers. So that means that either you have 3 people that know each other or mutually friends, or there are 3 people that completely doesn't know each other. Okay. Now here we focus our discussions on the graph. So a graph, what is a graph? So a graph is a mathematical structure that consisting of the several points or the nodes called the vertices, and also some line joining those edges, those vertices called the edges. So here we introduce some of the very important definition in the graph theory that can be very useful in our discussion. First of all, in a complete graph. So a complete graph, or denoted by the Kn, so it's a graph of order n. What I mean by order, that means that we have the n vertices, in which every 2 vertices form an edge. For every 2 vertices, we are joined by an edge. So a cycle graph, Cn, so it's a graph of order n, that means that we have n vertices that consisting of a single cycle. So all the complement of the graph, so the complement of the graph G is denoted by this bar G with the vertices. So then we have the same set of vertices, but the edges actually completely is a complement of each other. That means that if the one edge is appear in the graph G, then it does appear in the complement. So this is an example. So we can see that K4, so we have 4 dot, 1, 2, 3, and 4. And each of them, every pair of them are joined by an edge. And this is a C4, so we have the order 4. We have 4 vertices. And we have a single cycle on the from the graph. And this is a complement of C4. So we can see that this edges is rather appear in the C4. So this is in the complement. And similarly for these edges. Okay, so what is a Ramsey theory in graph? So Ramsey theory in graph, first we have the concept called the Ramsey numbers. So Ramsey numbers denoted by R, SD. So it's the minimum integer n such that for any two coloring of the edges of the complete graph Kn, that means that a complete graph with n vertices, then there must be a monochromatic subgraph, monochromatic subgraph which is a complete graph Ks or K of order S or order T. So monochromatic means that we have the same color. So here example is the R33 is equal to 6. So this is just like the typical example that I shown just now. Then in the group of the 6 people, we can either have 3 mutually strangers or 3 mutually friends. So this is an example. So let's say in we have a graph with a complete graph with 6 vertices, and we color each of them. Let's say the straight line is one color and the dotted line is another color. So we can see that we have the monochromatic. So this is a monochromatic K3 in the K6. Okay, now let us walk through a simple proof of the Ramsey number R33 is equal to 6. So hopefully after this, you have a clearer picture of what is mean by the Ramsey numbers. So first of all, in the K6, so we have 6 vertices. So now we focus on the vertex V. So note that in the complete graph, the vertex V must adjacent to another 5 other vertices. So now, imagine that you have the two color, let's say red and the blue. So you want to color these 5 edges. So it's very direct to see that at least 3 of them must have a same color. So let's say we assume that we have the 3 blue color. So the proof will be very similar. The argument will be very similar if we have the 3 red colors. So now, this is our let's say this is our coloring. Note that this will be always happening. This is always happening. The only difference that perhaps is either red or the blue. So now we focus on these 3 edges. So note that if one of these edges is colored with blue color, like this, or this, and this, then we always have a blue K3 in the graph. Otherwise, we have the red K3 in the graph. So this means that in whatever red-blue coloring of the K6, we will always have either the blue K3 or the red K3. So we have the R33 is at most 6. Now, to prove that 6 is the minimum, we need to construct an example of the K5 that have no monochromatic K3. So for example, if we color the K5 as shown here, where all the outer edges are colored with blue and all the inner edges are colored with red, then here we have no monochromatic K3. That means that our R33 is greater than 5. So combining these two, we show that the Ramsey number R33 is equal to 6. So here is some non-Ramsey numbers up to now. So you can see that here only the few that we already know the exact number. First we have R33. So similarly we have the R44. That means that in the group of 18, then we have either 4 mutually friends or 4 mutually strangers. But you can see that with R55, the result is still not exact. Also we get some boundary. So we can see that from this table, so we can see that we have still many gaps. So it can be improved. Okay, but more generally, we would not only looking at the subgraph as a complete graph as a graph subgraph. We could also see some general graph. There's a graph G or graph H. G or H can be any other graph, not necessarily a complete graph. Or analogously, we could see that the Ramsey number as the smallest integers such that for each graph of that particular order, then either the graph contain the G as a subgraph or the complement contain the H as a subgraph. So it's coming from, so here we have the monochromatic. Let's say if we have two colors, red and blue. So let's say we have the in the classical Ramsey number. So either we have the blue graph G or red graph H. So let's say we take out the graph G and we delete all the red edges. So this is how we can get the analogous definition of the Ramsey numbers. So now I'll introduce some type of graph that we are going to use in the discussion. So since we are focused on the tree and the well, so I'm going to give a definition on the tree and the well. First, tree graph Tn, denoted by Tn. So it's a connected graph of order n that containing no cycle subgraph. That means that containing no cycle. And a well graph is the graph consisting of the disjoint union of the K1 and Cn. So this is an example. So here we have the T7. So we can see that there is no cycle in our tree. And here this is a well graph W8. So we can see that we have this cycle C8 and the single K1, single vertex K1 here. And we joining all the vertices from the Cm to the K1. Okay. For this discussion, let's say we define our tree as what is shown here. So let's say Q1 up to Q3 is a T disjoint tree. That means that there are trees and that not are connected to each other. And with the total vertices in the Q1 up to Q3 is K plus 1. And each of them have at least 2 vertices. So let's say we arrange our tree as below. So let's say we not repeat the V naught with the maximum degree. And let's say this all is the degree 1 vertices here. That means that they are only adjacent to the V naught, but not joined with any other vertices. And here we call a branch, a bigger branch here, where we have T of them, Q1 up to Qt, and the total vertices here is K plus T. That means that if you excluded the V1 up to Vt, that means that we have total K vertices over here. Okay, if this K is at least 5, and the 3T is as what we defined just now, then there is a positive integer n naught such that for each integer n greater or equal to n naught, then the Ramsey numbers T Wx is equal to 2n minus 1. So the n k, when if also k is at least 5, so we can see that when this is a maximum degree, so if this is at least 5, at least k or at least k, so we know that this will have the degree of n minus k minus 1. So the maximum degree is n minus k minus 1. So there is a positive integer and not k such that for each n greater or equal to n naught, that means that if n is sufficiently large, then our Ramsey number RT W8 is equal to 2n minus 1. So this is our main result. Introduce some of we are going to omit the technical proof in this talk, but rather than I'm going to show you how we're going to get this very brief outline of how we're going to get this result. Okay, first of all, let's say K is at least 5, and let's say we only have one big branch here. So this Q must have at least one of these Z1 up to Z10 as a subgraph. So Z1 is when V1 is adjacent to at least 4 other vertices, and Z2 is when V1 is adjacent to exactly 3 of other vertices, and Z3 and Z4 is when V1 adjacent to 2 other vertices, and Z5 up to Z10 is when V1 is only adjacent to 1 other vertices in the Q. So if we have two big branch, Q1 and Q2, then the Q1, the disjoint union of Q1 and Q2 must have at least one of these four subgraph. And similarly, if we have at least three of the branch, I mean T is at least three, then all of and all this T1 up to T will contain this as the subgraph. Okay, now the next, let's say we have the K with any fixed any positive integer, and suppose that our T again T1 is a 3 defined in the definition 1. So the V of Q1 of course is at least 2. Then let's say we have the Q, we have a degree 1 vertices in the Q other than the vertices V1. So now let's say we have another tree Q1 prime, such that we just delete this vertices Q here. So this is something look like this. So we have we have V0 adjacent to V1. So here it can be adjacent to any other vertices. So at one point we have a vertices Q here. Or let me just draw something like this. So it can be adjacent to a series of vertices here. So we have a Q here. And then of course here we can have other vertices here. Now, let's say if we delete the Q. If we delete the Q, so this is our Q1 prime. And let's say T2 is a tree getting from T1 by deleting the vertex Q and also the edges. Then we say that if a graph with the order 2n-1 contain T2 but the complement doesn't contain WA, then the G must contain T1. So this is something we're going to omit the proof here. Next, if this result work for a single branch, then similarly we can apply it again and again on itself or other branch. Then we can have this. So we can delete all, I mean, turn by turn we can delete the degree 1 vertex from all other graph. Next, we have this a very interesting result here. So let G be a graph where the vertex we have the V1 up to V4. So this 4 vertex is rather adjacent to the U. So we have something like this. So this is a graph U. So this is a U with the order is n vertices here. We have n vertices here. N vertices. And we have 4 vertex here. V1, V2, V3, and V4. And all of this all vertices in the U that are adjacent to the E1, V2, V3, and V4. For we prove that for sub when n is large, when this n is large enough, then if a complement doesn't contain any WA, then we show that this graph, the n vertices here must contain graph that we have the with the subgraph of the tree that we define in the Z1 the Z1 up to Z15 that we defined just now. Okay, next we show that when n is sufficiently large, then if our tree is the tree defined such that our branch is exactly all the Z1 up to Z15 here, then the Ramsey number is actually 2n-1. Then by using this lemma, we know that whenever we add another new vertices to this tree, then the result will also the Ramsey number will also be 2n minus 1 because we know that if this tree this contain the T2, that means it contains this graph, then we add another vertex of degree 1 to all of this branch, then we also get the Tn minus 1. We also get the Ramsey number is 2n minus 1. So combining all of this, we get our main result. Okay, before we end our talk, I'm going to propose a open problem or for a conjecture. So that so this is a conjecture. So the Ramsey number of the Tn, the tree versus a well is 2n minus 1 for nearly all the tree graph when n is sufficiently large, and also when our m is even. That means that our well graph is on the k1 plus a even cycle. And this is a reference that we used in preparing the slide. First of all, this is the first reference is our main result, and this is also some of the proof. I'm going to use the result from one of our previous work, and this is the survey that is still updating. So it's now already on version 17. So if you're interested in these Ramsey numbers, feel free to. This is always for public access, so you can always go to this research to start work looking at some of the interesting results. And very proudly to say that there are some of our results also cited inside the survey. So that's all from my talks. Thank you for listening. So feel free to give any comment or any question. I will read it and answer them accordingly. And if you have think of anything about the Ramsey numbers or just some topic in the graph theory, feel free to contact me, and I'm very happy to have a discussion, and perhaps we can collaborate further, and hopefully we can have some fruitful output. So thank you.